Hi guys, my name is Luke Bennick and I'm here with 3Helix, and in this short video I just want to talk to you guys how you can use collagen hybridizing peptides in order to visualize fibrotic tissues. So this is a tissue staining application and where there's excess collagen production. So before we get started, I just want to give you a little bit of background on Collagen Molecule and our CHP. So collagen is based on a hierarchical organization where you have collagen fibers made up of these collagen fibrils that are made up of the collagen triple helical molecules. Now, the triple helix is made up of 3 individual alpha chains. Now, you can think of this as a piece of rope, and the piece of rope is made up of individual pieces of twine. And when the 3 pieces of twine come together, they can fold, and it offers it a lot more strength and stability. However, when the collagen triple helix is damaged at all, either by collagen remodeling that's on purpose for organ development, or mechanical overloading, enzymatic degradation, doesn't matter, the collagen triple helix that used to be strong and intact can now unravel and unwind. Now, as you know, a single piece of twine is not near as strong as all 3 pieces together as a rope. So when the collagen gets damaged, it is also weaker. However, this offers us a unique opportunity for targeting regions of collagen turnover. So we designed our collagen hybridizing peptide, or CHP, based on a repeating sequence of a glycine, proline, and hydroxyproline amino acids. Now, this peptide has a high affinity for going in and reforming that collagen triple helix. So, for example, we have this nice collagen fiber, and it gets damaged by a specific family of enzymes known as matrix metalloproteinases, or MMPs. So when the MMPs act on the collagen fiber, they can actually cleave the individual collagen triple helical molecules. And this leads to a bunch of single-stranded collagen exposed in the microenvironment. So what we did is we designed the CHP, and we were able to apply fluorescent tags or biotin onto it. And with this CHP now labeled, we can actually stain collagen, and they will readily form these triple helices with regions where there's single-stranded collagens. So going back to our first example, we have a nice, healthy, intact collagen fiber, or collagen triple helix. It gets damaged and begins to unfold and unwind, and then we have a very small peptide sequence with a fluorescent probe or biotin on it that can go in and reform the collagen triple helix and stay bound in that state. And then this allows you to visualize regions where there's high collagen turnover or high collagen remodeling. Now, you can think of the CHP binding to the collagen strands the same way as DNA in PCR. So you have these DNA primers that are very short, and they can hybridize with the much larger sections of DNA during PCR. So what we thought is, okay, now we have this fluorescent probe or this biotin attached to our CHP that can refold into the collagen triple helix. So we wanted to know, can we target damaged collagen within tissues, and is there collagen remodeling within the tissue? And we would like to answer these questions and then compare it to common stains such as H&E. So the answer to both the questions is yes, there is damaged collagen or denatured collagen within tissue samples, and we are able to target it and bind to it with our collagen hybridizing peptide. So in this example, this is pulmonary fibrosis, where you have an excess of collagen production, and it forms scarring within the lungs. As you can see here, when you look at our CHP stained in red, you see regions where there's high collagen turnover and high collagen remodeling. When you compare it to a healthy tissue here, you can only see the DAPI, and there's really not any CHP binding. And this is because the collagen in this model is still in a triple helical form, and there's no way for our CHP to bind. And this example is done in a mouse lung tissue. We took it a step further, and we looked at 2 different zones within the lung, the central part and the subpleural part. And we monitored the disease, or we monitored the formation of fibrotic tissue over time. And what we saw is, as time increased, we saw more and more collagen remodeling and more fibrotic tissue forming. But what we also noticed is there is a much higher level of collagen remodeling in the subpleural region. And these fluorescent images, we were actually able to quantify this and show that there is a distinct difference between the amount of collagen remodeling within the subpleural region versus the central region. And you can also see that there is an increase in collagen remodeling over time, letting us know that there is more and more fibrotic tissue forming. Again, this experiment was done in mouse lung. Now the next example is actually done in human tissues. So this is a liver fibrosis model that is based on biliary atresia, which basically is caused by blockage in the bile ducts within the liver. Now patients with BA oftentimes require surgery to correct this, and if they don't get surgery, it oftentimes results in death, or they require a liver transplant. So what you see here is this is a human liver wedge biopsy, and in the top example we have a liver section that the patient did actually require a liver transplant even after they did the surgery. As you can see, there's high levels of CHP binding as imaged here in the green fluorescence channel, and when you compare that to a patient that underwent the surgery to fix BA, this sample, the patient did not have to get a liver transplant, and you see much lower levels of CHP intensity or CHP binding in this sample. So what we were able to do, the clinicians were able to score this signal intensity, quantify this signal intensity and compare it to the Medivir scoring system already in place for liver fibrosis. So a score of 3 and 4 is very fibrotic, and what we have here is the patients that went into surgery with a Medivir score of 3 or 4, and then after the surgery they did the biopsy. These two scores, the patients did not require a transplant, and you can see there's very little CHP signaling. However, in patients that did require a liver transplant even after the surgery, you can see much higher levels of CHP intensity, indicating that there is still a lot of fibrotic tissue in the liver. So these are two different examples. One was in mouse lung, and the other was in a human tissue, human liver tissue. And we can see that CHPs can easily detect the collagen remodeling as a result of excessive collagen production in fibrotic tissues, whether it be mouse or human. So again, they can be applied to numerous species. CHPs can be useful in monitoring the disease progression over time, as I showed in the pulmonary fibrosis. Over the course of time, you saw the amount of collagen remodeling increase. And then CHPs are actually a very simple to use stain, and you're actually able to co-stain it with other stains such as DAPI and other antibodies. So if you have any other questions, again, my name is Luke Bennick. You can contact me here. And I wanted to introduce a few other members of our team that you also would be contacting. If you needed to order any more CHPs, please contact Helen. Or if you had any good applications or had new ideas for a partnership, please contact our business development, Dr. Mike Kurtniks. Thank you very much. Have a good day.